Hey everyone, welcome back. This explainer is brought to you by Forge College. And man, we are so excited to continue our journey through the Solidity from Zero track. Now, if you remember our previous lesson, using mappings with structs, we unlocked this massive superpower, right? The ability to store complex custom data types directly inside a smart contract mapping. But it kind of left us hanging with a really big question. What happens when our data isn't just a simple single-level list? What if we need to store multi-dimensional data? Think about a scenario where an owner has multiple token IDs, and every single one of those IDs has its own specific metadata. Well, grab your coffee, because today we are solving exactly that problem. All right, here's the game plan for today's explainer. First, we'll hit the multi-key dilemma. Next, we'll break down nested mappings, followed by the main alternative, hashed composite keys. After that, we're going to navigate the super tricky phantom zero trap, figure out which method actually wins in a head-to-head showdown, and finally, wrap up with how to test and verify everything. Section 1. The multi-key dilemma, when one key isn't enough. Okay, so think of your standard single key mapping like a simple filing cabinet drawer. You stick a label on a file, you pull it out, and boom, there's your data. Super efficient, right? But as your decentralized apps get bigger and more complex, that single drawer is literally going to start overflowing. So picture this. How do you find one specific file in a massive digital warehouse when you need to use more than one label to identify it? Like, say you need to look up a record using both a user's wallet address and a specific numeric ID. Just slapping a single label on a folder isn't going to cut it anymore. We need a totally new system. Basically, we either need to start putting folders inside of our drawers, or we need to invent a brand new kind of combined barcode that scans both pieces of info at the exact same time. Moving to Section 2, nested mappings. Basically, folders within drawers. I actually like to call this the inception method of data storage. It's literally a mapping within a mapping. Look at the syntax here. A mapping of an address to another mapping of a uint 256 to a record. In Solidity, this nested mapping trick lets a key point directly to a whole other mapping. It creates this beautifully transparent storage layout that perfectly preserves your original key types, so an address and a uint 256 in this case. And honestly, it makes two-key lookups incredibly straightforward. If you want the metadata for user A's token number 5, you literally just ask the contract for the record at address A, ID 5. It feels completely natural, it's super readable, and the compiler handles all the heavy lifting of finding exactly where that data lives in the blockchain storage. All right, Section 3, hashed composite keys, or what I like to call the blender method. Now, what if you're not a fan of the mapping inside a mapping inception stuff? What if you want to keep your top-level storage totally flat? Well, instead of nested folders, we use this blender method to melt two distinct labels, like our owner address and token ID, into one unique flattened identifier. We do this using Ketchak 256 wrapping abi.encodePacked with the owner and ID. This cryptographic hash function takes those two separate keys, blends them together, and spits out a single uniform bytes 32 key. The really cool part here is that your mapping stays perfectly flat. You just have one single mapping that takes that bytes 32 hash and hands you back a record. It simplifies your storage surface dramatically. But it does introduce an explicit math step. You've got to compute that hash every single time you want to store or look up a record. Which brings us to Section 4, the phantom zero trap, aka Solidity acting like a very literal robot butler. Okay, to really get this, you have to understand that Solidity is basically an incredibly literal robot butler. If you ask it to fetch a record from a mapping, and that record doesn't actually exist yet, it doesn't complain. It doesn't throw an error or give you a null or undefined warning like JavaScript might. Nope, Solidity just calmly hands you a blank 0. It's basically saying, well, you didn't save anything here, so I assume you meant exactly 0. Now, this default value ambiguity is pretty hilarious until it completely breaks your smart contract logic. Imagine storing account balances. If you ask for an unregistered user's balance, Solidity hands you a 0. But wait, what if a registered user legitimately just has a 0 balance? How on earth do you tell the difference between missing data and actual data that just happens to be 0? And here is the absolute hero of our story, the explicit exists Boolean flag. Listen, whether you're using nested mappings or hashed keys, you absolutely must add a simple Boolean flag to your custom struct. When you save real data, you flip that exists flag to true. So now when you retrieve a record and the value is 0, you just check the flag. If exists is false, you know for sure the data is missing. If it's true, you know it's a legitimate verified 0. Seriously, it's a tiny little addition, but it will save you from massive headaches down the road.
Section 5. Which method wins? Nested versus hashed.
Let's set up a quick head-to-head showdown so you know exactly which tool to pull from your developer belt. When we look at lookup syntax, nested mappings are super intuitive. You literally just use bracket notation twice. Easy. Hashed keys, on the other hand, require you to call that hashing function first. For access patterns, nested mappings are incredibly gas-optimal when you're frequently querying using both keys together. It's just built right into the language structure. But hash composite keys really shine when you want a single unified mapping interface, or if your keys are already bundled together as a tuple anyway. Now, gas tradeoffs are generally pretty comparable for storing, but keep in mind that extra Keka256 hashing step does add a tiny bit of computational overhead to your read and write calls. But hold on, there is a really crucial warning for the Blender method. Look closely at abi.encodePacked versus abi.encode. If you are hashing variable length data types, like say 2 strings, you absolutely must prefer abi.encode. Why? Because EncodePacked just blindly jams the bytes together. Think about it. If you pack the strings A and BC, it becomes ABC. But if you pack the strings A, B, and C, it also becomes ABC. That is what we call a hash collision, and it means 2 entirely different users could accidentally overwrite each other's data. Yikes. Using abi.encode adds proper padding and linked prefixes to absolutely guarantee you prevent those packing collisions.
Section 6. Test and verify. Build, iterate, validate.
Okay, so we know the theory. Let's move into the practical validation phase. How do we actually confirm our multidimensional storage works in the wild? You need to memorize this 3-step testing mantra. First, store the record. Second, retrieve the record and make sure the values match. And third, and this is the most important one, check a missing key. I really cannot emphasize this enough. Checking a completely uninitialized key is literally the only way to prove your existence flag is actually working and returning false when it's supposed to. Before you even think about deploying this code, please run through these technical checkpoints. Number 1, check your compilation and ABI to make sure your getter functions are actually visible. 2, verify round-trip storage, ensuring that whatever goes in is exactly what comes out. 3, validate non-existent lookups to test that phantom 0 trap we talked about. 4, do a collision sanity check, especially if you're hashing strings or dynamic arrays. And 5, run a quick gas measurement. Just double-check if your chosen method is needlessly burning gas for your specific use case. If you pass these checkpoints, you can deploy with complete developer confidence. And finally, wrapping up, preparing for pitfalls. So, the absolute core rule of thumb you should take away from this explainer today is this. Always, always use an existence flag. Whether you decide to go with the nested folders method or the hashed barcodes method, that simple Boolean flag is your ultimate source of truth in a smart contract. So what do you think? Are you ready to hunt down some mapping bugs? Now that you fully understand how to structure this complex data, you are perfectly positioned for our next lesson, mapping pitfalls and debugging patterns, where we're going to break things on purpose just to see how to fix them. Thank you so much for joining me on this explainer, and hey, remember to visit forge.college to dive deeper into this subject, master these Web3 topics, and continue your journey from zero to expert. Keep building, and I'll see you in the next one.